Use of wood in buildings and bridges, prepared by Aljon Pakapat and Loreda Camarillas.
Light frame buildings. Historically, two general types of light frame construction have been used: balloon and platform framing. Balloon framing, which was used in the early part of 20th century, consists of full height wall framing members for two-story construction. Additional information of balloon framing is available for older construction manuals. Since the latter part of 20th century, platform framing has dominated the housing market, is widely used in commercial and light industrial applications. Platform framing features the construction of each floor on top of the one beneath. Platform framing construction differs from the part of 60 years ago in the use of new and innovative materials, panel products for floor and roof sheeting, and prefabricated components and modules as opposed to stick-built or on-site construction. So foundation. Light frame buildings with the basements are typically supported on cast-in-place concrete walls or concrete block walls supported by footings. This type of construction with a basement is common in northern climates. Another practice is to have concrete block foundation extend a short distance above ground to support a floor system over a crawl space. In southern and western climates, some buildings have no foundation. The walls are supported by a concrete slab, thus having no basement or crawl space. Treating wood is also used for basement foundation walls. Basically, such foundation consists of wood frame wall sections with studs and plywood sheeting supported on the treated wood plates, all of which are preservative treated to as a specified level of protection. To distribute the load, the plates are laid on a layer of crushed stone or gravel. Walls, which must not be designed to resist the lateral loads of the backfill, are built using the same technique as conventional walls. The exterior surface of the foundation wall below grade is draped with a continuous moisture barrier to prevent direct water contact with the wall panels. The backfill must be designed to permit easy drainage and provide drainage from the lowest level of the foundation. Because of a foundation wall needs to be a permanent, the preservative treatment of the plywood and framing and the type of fastener used for the connection is very important. Floor. For houses with basements, the central supporting structure may consist of wood posts on suitable footings that carry a built-up girder, which is frequently composed of planks that the same width as the joints. Standard 38 by 184 mm to 38 by 286 mm, nominal 2 by 8 inch to 2 by 12 inch. Face nailed together and set on edge. Because planks are seldom sufficiently long enough to span the full length of the beam, butt joints are required in the layers. The joints are staggered in the individual layers near the column support. The girder may also be a glulam beam or a steel I-beam, often supported on adjustable steel pipe columns. Similar details may be applied to a house over a crawl space. The floor framing on a residential structure typically consists of wood joists on 400 or 600 mm, 16 or 24 inch, center support by a foundation wall, and the center girder. Joist size depends on the anticipated loading, spacing between joists, the distance between support or span, species and grade of the lumber. Commonly used joists are standard 38 by 184 mm or 38 by 235 mm, nominal 2 by 8 inch or 2 by 10 inch lumber. Prefabricated wood I-joist or parallel cord trusses. Lumber joists typically span from 3.6 to 4.8 meters or 12 to 16 feet. Preferably, such openings are parallel to the length of the joist to reduce the number of joists that will be interrupted. At the interruption, support header is placed between the uninterrupted joists and attached to them. A single header is usually adequate for the opening about 1.2 meters or 4 feet in width, but double headers are required for wider openings. Special care must be taken to provide adequate support at headers using joist hanger, for example. Cutting of framing members to install items such as plumbing lines and heating ducts should be minimized. Cutting members may require a reinforced scab, or a supplementary member may be needed. Areas of highly concentrated loads, such as under bathtubs, require doubling of joists or other measure to provide adequate support. One advantage of framing floors will be parallel cord trusses or prefabricated I-joists is their long span capabilities may eliminate the need for interior supports. An additional advantage is that the web areas of these components are designed for easy passing of plumbing, electrical, and heating ducts. Floor sheeting or subflooring is used over the flooring framing to provide a working platform and a base for finished flooring. Older homes have a board sheeting, but newer homes generally use panel products. Common sheeting materials include plywood and OSB, are available in a number of types to meet various sheeting requirements. Exterior type panels with water resistance adhesive are desirable in locations where moisture may be a problem, such as floor near plumbing fixtures or situations where the subfloor may be exposed to the weather for some time during construction. Plywood should be installed with a green direction of the pale plies at right angles to the joist. Oriented strand board also has a preferred direction of installation. Exterior walls. Exterior walls of light frame structures are generally load bearing. They support upper floors and the roof. An exception is the cable ends of one or two-story building. Basically, wall framing consists of vertical studs and horizontal members, including top and bottom plates and header or lintels, over window and door openings. The studs are generally standard 38 by 89 mm, 38 by 114 mm, or 38 by 140 mm. Nominal 2 by 4 inch, 2 by 5 inch, or 2 by 6 inch member space between 300 and 600 mm, 12 and 24 inch on center. The selection of the size depends on the load the wall will carry, the need for support of wall covering materials, and the need for insulation thickness in the walls. Headers over openings up to 1.2 meters or 4 feet are often 38 by 140 millimeters or 2 by 6 inch. Nailed together, face to face with spacers to bring the headers flush with the face of the stud. Special header that match the wheel thickness are also available in the form of either prefabricated I-joist or structural composite lumber. Wall framing is erected over the platform formed by the first floor joist and subfloor. In most cases, an entire wall is framed on a horizontal position on the subfloor, then tilted into place. If a wall is too long to make this procedure practical, sections of the wall can be formed horizontal and tilted up, then joined to adjacent sections. Corner studs are usually prefabricated in such a configuration as to provide a nailing edge for the interior finish. Studs are sometimes double at the points of intersection with an interior partition to provide backup support for the interior wall finish. Alternatively, a horizontal block is placed high-mid between exterior studs to support the partition wall. In such a case, backup clips on the partition stud are needed to accommodate the interior finish. Upper plates are usually doubled, especially when rafters or floor joists will bear on the top plate between studs. The second top plate is added in such a way that it overlaps the first plate and corners and interior wall intersections. This provides a tie and additional rigidity between the wall floor framing and sill plate that should be anchored to the foundation. If a second story is added to the structure, the edge floor joist is nailed to the top wall plate and subfloor and wall framing added in the same way as the first floor. Sheeting for the interior wall is commonly some type of panel product. Here again, plywood or OSB may be used. Fiberboard that has been treated to impart some degree of the water resistance is another option. Several types of fiberboards are available. Regular density boards sometimes require additional bracing to provide the necessary resistance to lateral loads. Intermediate density board is used when structural support is needed. Numerous foam-type panels can also be used in part greater thermal resistance to the walls. Ceiling and roof. Roof systems are generally made of either the joist and rafter system or trusses. Engineered trusses reduce on-site labor and can span greater distances without intermediate support, thus eliminating the need for interior load carrying partitions. This provides greater flexibility in the layout of interior walls. Prefabricated roof trusses are used to form the ceiling and slope roofs of more
than two-thirds of current light frame buildings. For residential buildings, the trusses are generally made using standard 38 by 89 mm or nominal 2 by 4 inch lumber and metal plate connectors with the teeth that are pressed into the pieces that form the joints. Joints and the rafter systems are found in the most buildings constructed prior to 1950. Rafters are generally supported on the top plate of the wall and attached to a ridge board at the roof peak. However, because the rafter slope, they tend to push out the tops of the wall. This prevents the nailing to the rafters to the ceiling joist and nailing the ceiling joist to the top wall plates. A valley or hip is formed where two or roof sections meet perpendicular to each other. A valley rafter is used to support short-length jack rafters that are nailed to the valley rafter and the ridge board. In some cases, the roof does not extend to a gable end, but is sloped from some point down to the end wall to form a hip. Roof are hip rafter supports to the jack rafters, and the other ends of the jack rafter are attached to the top plates. In general, the same materials used for the wall sheeting and subflooring are used for the roof sheeting. Wood deck. A popular method of expanding the living area of a home is to build a wood deck. Adjacent to one of the exterior walls, decks are made of preservative-treated lumber, which is generally available from local building supply dealers and depending upon the complexity, may be built by the to-do-it-yourselfer. To ensure long life, acceptable appearance, and structural safety, several important guidelines should be followed. Proper material selection is the first step, then proper design and construction techniques are necessary. Finally, proper maintenance practices are necessary. Post frame and pole buildings. In post frame and pole buildings, round poles or rectangular post serves both as the foundation and the principal vertical frame element. This type of construction was known as pole buildings, but today, with extensive use of posts, is commonly referred to as post frame construction. For relative low structures, light poles and roofing framers are nailed to poles or posts set as fairly frequent centers, commonly 2.4 to 3.6 meters or 8 to 12 feet. This type of construction was originally used with round poles for agricultural buildings, but the structure principle has been extended to commercial and residential buildings. Round poles present some problems for connecting frame members. These problems can be eased by slabbing the outer face of the pole. For corner poles, two faces may be slabbed at right angles. This permits better attachment of both light and heavy framing by nails or timber connectors. When the pole is left around, the outer face may be notched to provide seats for beams. Rectangular posts are the most commonly used and may be solid stone glow lamp or built up by the nail laminating. Built-up posts are advantageous because only the base of the post must be preservative treated. The treated portion in the ground may have lamination of various lengths that are matched with the lengths of untreated laminations in the upper part of the post. The design of the types of posts must consider an integrity of the splice between the treated and untreated lumber. The wall systems consist of horizontal girts, often covered with a light gauge metal that provides some degree of rocking resistance. Roof trusses made with the metal connectors are attached to each pole or post. A roof's purlin are installed perpendicular to the trusses at spacing from 1.2 to 3.7 meters or 4 to 12 feet, with 2.4 meter or 8 feet as common spacing. For 2.4 meters, 8 feet truss spacing, these purlins are often standard 38 by 89 mm or nominal 2 by 4 inch, spaced on 0.6 meter or 2 feet centers and attached to either the top of the trusses or between the trusses using joist hanger. Log buildings. Interest is growing on log houses from small, simple houses for vacation use to large, permanent residences. Many US firms specialize in the design and materials for log houses. Log houses nearly always feature wall systems built from natural or manufactured logs rather than from dimensional logs. Roof and floor systems may also be built with logs or conventional framing. Log house companies tend to categorize log types in two systems, round and shape. In the round log system, the logs are machined to a smooth, fully rounded surface and they are generally all the same diameter. In the shape system, the logs are machined to specified shapes, generally not fully round. The exterior surfaces of the logs are generally rounded, but the interior surface may be either flat or round. The interface between logs in the machine to form an interlocking joint. Consensus standards have been developed for along grading and assignment of allowed properties, and these standards are being adapted to building codes ASTM 2009. Builders and designers are need to realize that logs can reach the building sites at moisture content levels greater than ideal. Heavy timber buildings. Heavy timber construction is a building method that uses large, rustic, heavy sawn timbers or structural glue laminated lumber that is joined together with traditional mortise and tenon jointry or modern metal jointry. Timber frame. Timber frames houses are common in early America and enjoying some renewed popularity today. Most barns and factory buildings dating prior to the middle of the 20th century were heavy timber frames. The traditional timber frame is made of large sawn timbers, larger than 114 by 114 millimeter or 5 by 5 inches, connected to one another by hand fabricated joints, such as mortise and tenon. The construction of such a frame involves rather sophisticated joinery as illustrated. In today's timber frames a home, a prefabricated composite sheeting panel 1.2 by 2.4 meter or 4 by 8 feet is frequently applied directly to the frame. This panel may consist of an inside layer of 13 millimeter or 1/2 inch gypsum, a core layer of rigid foam insulation, and an outside layer of exterior plywood or OSB. Finished siding is applied over the composite panel. In some cases, a layer of standard 19 millimeter or nominal 1 inch pang and groove solid wood boards are applied to the frame, and a rigid foam exterior plywood composite panel is then applied over the boards to form the building exterior. Mill type. Mill type of construction uses timbers of large cross sections with columns spaced in a grid according to the available lengths of beam and girder timbers. The size of the timbers make this type of construction resistant to fire. The good insulating qualities of wood, as well as the char that develops during fire, results in slow penetration of fire into large members. Thus, the members retain a large proportion of the original load carrying capacity and stiffness for a relatively long period after the onset of fire. To be recognized a mill-type construction, the structural element must meet specific size. Columns cannot be less than standard 184 millimeter or nominal to 8 inches in dimensions, and beams and girders cannot be less than standards 140 by 235 millimeter or nominal 6 by 10 inch in cross-section. Other limitation must be observed as well. Glulam beam. This system is based on supporting columns located at the corners of pre-established grids. The main glulam beams support purlins which may be sawn timbers. Glulam parallel coarse trusses or prefabricated wood I-joists. These purlins, which are normally 2.4 meter or 8 feet centers, support pre-frame structural panels. The basic unit of the pre-frame system is 1.2 by 2.4 meters or 4 by 8 feet. Structural panels nailed to a standard 38 by 89 millimeter or 38 by 140 millimeter, nominal by 2 by 4 inch or 2 by 6 inch stiffeners, sub-purlins. These stiffeners are run parallel to the 2.4 meter or 8 feet dimensions of the structural panel. One stiffener is located at the center line of the panel. The other is located at the edge, with the plywood edge at stiffener center line. The stiffener are pre-cut to a length equal to the long dimension of the plywood, less the thickness of the purlin, with a small allowance for the hanger.
Arc structures. These are particularly suited to applications in which large, unobstructed areas are needed, such as churches, recreational buildings, and aircraft hangars. Many arc forms are possible with a variety limited only by the imagination of the architects. Churches have used arcs from the beginning of glula manufacture in the United States. Dome. Radial rib domes consist of curved members extending from the base ring or tension ring to a comparison ring at the top of the dome along with the other ring members at various elevation between the tension and comparison rings. The ring members may be curved or straight. If they are curved to the same radius as the rib and have their centers at the center of the sphere, the dome will have a spherical surface. If the ring members are straight, the dome will have an umbrella look. Connections between the ribs and other ring members are critical because of the high compressive loads in the ring members. Other dome patterns called varaks and triacs, are also used. Timber bridges. Prior to the 20th century, timber was the major material used for both highway and railroad bridges. The development of steel and reinforced concrete provided other options, and these have become the major bridge building materials. However, the U.S. inventory does contain a substantial number of timber bridges, many of which continue to carry loads beyond their design life. A recent initiative in the United States has focused research and technology transfer efforts on improving the design and performance of timber bridges. As a result, hundreds of timber highway bridges were built across the United States during the past several years, many using innovative designs and materials. Moreover, bridges consist of a substructure and a superstructure. The superstructure consists of abutments, piers, or piling, and it supports the superstructure that consists of stringers and or a deck. Log stringer. A simple bridge type that has been used for centuries consists of one or more logs used to span the opening. Several logs may be laid side by side and fastened together. The log stringer bridge has been used to assess logging areas and is advantageous when adequate sized logs are available and the bridge is needed for only a short time. Unless built without durable species, the lifespan of a log stringer bridges is usually limited to less than 10 years. Attic construction with conventional rafters and ceiling joists or roof trusses can be insulated between framing members with batt, blanket, or loose fill insulation. In some warm climates, radiant barriers and reflective insulations can provide an additional reduction in cooling loads. Sawn lumber. Several types of bridges can be built with sawn lumber. Even though the span is usually limited to about 9 meters or 30 feet because of the limited size of the lumber available, this span length entails the majority of timber bridges in the United States. Several timbers can be used to span the opening, and a transverse lumber deck can be placed over them to form a stringer and deck bridge. Lumber can be placed on edge, side by side, and used to span the entire opening, forming a longitudinal deck bridge. The lumber can be fastened together with the nails or large spikes in the partial width panelized bridge systems, or compressed together with high-strength tension rods to form a stress-laminated slab-type deck. Glulam. Structural glued laminated or glulam timber greatly extend the span capabilities of the same types of bridges described in the previous paragraph. Glulam stringers placed 0.6 to 1.8 meters on center can support a glulam deck system and results in a span of 12 to 30 meters or more. Using glulam panels to span the opening results in a longitudinal deck system, but this is usually limited to about 9 meter spans. These panels are either interconnected or supported at one or more locations with transverse distributor beams. Glulam beams can be used to form a solid deck, and curved glulam members can be used to produce various aesthetic effects and long-span bridges. Structural composite lumber. Two types of structural composite lumber, or SCL, laminated veneer and oriented strand, are beginning to be used to build timber bridges. Most of the same type of bridges built with either solid sawn or glulam timber can be built with SCL. Considerations for wood buildings. Many factors must be considered when designing and constructing wood buildings, including structural, insulation, moisture, and sound control. The following section provide a brief description of the design considerations of these factors. Structural. The structural design of any building consists of combining the prescribed performance requirements with the anticipated loading. One major performance requirement is that there is an adequate margin of safety between the structure's ultimate capacity and the maximum anticipated loading. Thermal insulation and air infiltration control. For most U.S. climates, the exterior envelope of a building needs to be insulated either to keep heat in the building or prevent heat from entering. Wood frame construction is well suited to application of both cavity insulation and surface applied insulation. The most common materials used for cavity insulation are glass fiber, mineral fiber, cellulose insulation, and spray applied foams. Moisture control. Moisture sources for building can be broadly classified as follows: surface runoff of precipitation from land areas, groundwater or wet soil, precipitation or irrigation water that falls in the building, indoor humidity, outdoor humidity, moisture from use of wet building materials or construction under wet condition, and errors, accidents, and maintenance problems associated with indoor plumbing. Water can change phase and can be transported over space by various mechanisms. Moisture accumulation within a building or within parts of a building can affect human comfort and health, influence building durability, and necessitate maintenance and repair activities. Furthermore, moisture accumulation in the building's thermal envelope is also likely to influence the building's energy performance. Some problems associated with moisture accumulation are easily observed: mold, mildew, dust mites, and human health. Mold and mildew in buildings are offensive, and the spores can cause respiratory problems and allergic reactions in humans. Mold and mildew will grow on most surface if the relative humidity at a surface is above a critical value and the surface temperatures are conducive to growth. The longer the surface remains above this critical relative humidity level, the more likely mold will appear. Paint failure and other appearance problems. Moisture trapped behind paint films may cause failure of the paint. Water or condensation may also cause streaking or staining. Excessive swings in moisture content of wood-based panels or boards may cause buckling or warp. Excessive moisture in masonry and concrete can produce efflorescence, a white powdery area, or lines. Structural failures. It is caused by a decay of wood, are rare but have occurred. Decay generally requires wood moisture content equal to or greater than fiber saturation. And temperatures between 10 and 43 degrees Celsius, wood moisture content levels above fiber saturation are only possible in green lumber or by absorption of liquid water from condensation, leaks, groundwater, or other saturated materials in contact with the wood. To maintain a safety margin, 20% moisture content is sometimes used during field inspection as a maximum allowable level. Effect on heat flow. Moisture in the building envelope can significantly degrade the thermal performance of most insulation materials, but specifically the thermal resistance of fibrous insulation and open cell foams. The degradation is most pronounced when daily temperature reversals across the insulation drive moisture back and forth through the insulation. Moisture control strategies. Strategies to control moisture accumulation fall into two general categories. First is minimize moisture entry into the building envelope, and second is provide for removal of moisture from the building envelope. Inasmuch as building materials and assemblies are often wetted during construction, design strategies that encourage dissipation of moisture from the assemblies are highly recommended. Sound control. An important design consideration for residential and office buildings is the control of sound that either enters the structure from outside or is transmitted from one room to another. Wood frame construction can achieve levels of sound control equal to or greater than more massive construction, such as concrete. However, to do as requires designing for both airborne and impact noise insulation. Airborne noise insulation is the resistant transmission of airborne noises, such as traffic or speech, either through or around an assembly such as wall. Noises create vibration on the structural surface that they contact, and the design challenge is to prevent this vibration from reaching and leaving the opposite side of the structural surface. Sound transmission class, or STC, is the rating used to characterize airborne noise insulation. So wall system with a high STC rating is effective in preventing the transmission of sound. Impact noise insulation is the resistance to noise generated by footsteps or dropping objects. Generally, addressed at floor-ceiling assemblies in multifamily dwellings. Impact Insulation Class or IIC is the rating used to characterize the impact noise insulation of an assembly. Both the character of the flooring material and the structural details of the floor influence the IIC rating.